Good day, ladies and gentlemen. My name is Krumb. I am a student research assistant at Technische Universität Darmstadt, Germany, and it is my pleasure to present to you today our joint work on using CycleGAN for online error compensation in electromagnetic tracking. In endovascular aneurysm repair, the current gold standard for intraoperative navigation is fluoroscopic X-ray imaging. Fluoroscopic X-ray imaging provides the surgeon a continuous means of accurate navigation while still maintaining visual cues like anatomical structure as well as the guide wire that is used during the procedure. However, fluoroscopic X-ray imaging also comes with a radiation exposure not only to the patient but also to the surgeon who has to work with this technology on a daily basis. Opposed to that, there are technologies such as electromagnetic tracking, or EMT for short. EMT also provides continuous navigation, but opposed to fluoroscopic X-ray imaging, does not expose the patient or the surgeon to dangerous ionizing radiation. However, EMT does not provide any visual cues, and also the accuracy can be degraded by metallic objects or magnetic objects in the vicinity of the tracker. Therefore, we aim for a hybrid scenario where we combine both X-ray imaging and electromagnetic tracking to perform both tracking modalities in an interleaved fashion, where only X-ray snapshots are taken instead of continuous X-ray imaging. And in between these snapshots, the EMT is used for continuous navigation. This minimizes the radiation exposure while still maintaining visual knowledge about the aorta and about the guide wire that is being used. However, metallic accuracy is still a problem, and it becomes even worse in this hybrid scenario because with a C-arm in presence of the electromagnetic tracker, the C-arm which has a steel enclosure, the metallic distortion also increases. And this is what we want to address in our work. So our contributions are an online compensation approach for electromagnetic tracking. Online, in this case, means that this approach only needs to be trained, or calibrated if you will, only needs to be trained once. So there is no training necessary to be performed in the operating room before the actual intervention. So we can consider this an out-of-the-box approach. Our approach is inspired by CycleGAN, so it uses adversarial neural networks for generating a compensation. Finally, we evaluate our approach in a phantom study, where we see that it outperforms our previous approach. Our methods start with a data acquisition routine, where we employ a Trackstar 3D guidance system as a magnetic tracking system. The Trackstar 3D guidance is a direct current electromagnetic tracking system, which also provides a quality estimate, or distortion estimate if you will. For data acquisition, we use a Type 180 sensor, which is a sensor with a diameter of 1.8 millimeters. It has to be noted that only one single sensor is used, and we do not use any auxiliary sensors for the compensation. We placed this tracker in the vicinity of a Zeem Vision RFD C-arm, which has a steel enclosure that generates magnetic distortion. And for the actual data acquisition, we use a calibrated plastic brick phantom that is placed close to the C-arm at different positions, and we use this calibrated plastic brick phantom to collect data in 3 different positional degrees of freedom. And using this whole framework and this whole setup, we generate different data sets. One data set from the laboratory, which has 60 points, collected in a clean laboratory environment without any significant sources of metallic or magnetic distortion. This also reflects in the tracking error that we measure in this environment. The other data sets, with a total of 480 data points, are collected in different C-arm environments. Some of them are relatively close to the C-arm, others are far apart from the C-arm. And some of the datasets were also collected in different orientations of the C-arm. All of the measurement points are results of 500 samples being averaged in static measurements. And something that also has to be noted is that all of these measurements are C-arm agnostic. So we do not store the C-arm orientation and position with respect to the electromagnetic tracker. So this is not a feature that we use in our approach. Our compensation architecture is inspired by CycleGAN, which means that it consists of two different GAN architectures. The idea here is, the overall idea is to treat the problem of error compensation as a domain adaptation problem, where we have the bedside domain with the C-arm in presence, as well as the bench-like domain, which is the laboratory domain without C-arm. And we translate from the C-arm domain to the laboratory domain because the laboratory domain obviously has less distortion and thus the navigation error is less. So as an input for both of these GAN architectures, we have the X, Y, and Z components measured by the electromagnetic tracker, as well as the orientational angles around the X, Y, and Z axis. We also provide the quality estimate that I have mentioned earlier as an additional input feature to learn the distortion and the associated deviation in the X, Y, and Z direction. At the output side, we only have the compensated Z-axis because mainly the most distortion reflects on the Z-axis of our results. For inference, we only use the generator, which generates points from C-arm points as an input to laboratory points. Similar to the original CycleGAN implementation, we employ an adversarial loss that reflects how well the generators can fool their associated discriminators. So this adversarial loss is the sum of two adversarial losses for each of the two GANs. To connect both of these GANs, similar to the original CycleGAN implementation, we employ a cycle loss function, which ensures cycle consistency by adding two recovery losses. The idea of the recovery loss is that given a certain input, for example from the laboratory domain, being propagated through both of the generators should in the end yield the original point that we initially passed into the network. Coming to the results of our approach. If we take a look at paired data from both the laboratory and the C-arm, we can see that the uncompensated C-arm points are dragged towards their laboratory equivalents, which are marked here as gray dots. So even for laboratory points that were not included in the original training set, which are denoted here as white circles, we see that the uncompensated points, the red C-arm points, are dragged towards the laboratory equivalents, which gives us a hint that the network is able to generalize very well. Also, in a quick ablation study, we see that our CycleGAN approach outperforms a simple GAN approach for domain translation, and adding a small fine-tuning step, which is tailored to the laboratory domain, also brings a little boost in accuracy. Finally, we evaluate our setup in a phantom study, where we use a glass phantom in the vicinity of a C-arm. And inside the glass phantom, there sits a little sensor of the electromagnetic tracking system, which is dragged using a custom 3D printed fixture, which is moved on a Lego board in steps of 8 millimeters. And yeah, giving the results of this phantom study, we see that our CycleGAN outperforms our previous artificial neural network approach and also provides better results than the original measurements. This we can also visualize in an animated video where we see how the sensor is pulled back through the aortic phantom, and the black dot that you see here is the sensor, how it appears on the X-ray image. And we see that for almost all of the positions, the CycleGAN compensation is perfectly in line with the actual sensor. Coming to a conclusion, we presented an online single sensor compensation approach for electromagnetic tracking, which does not require any data collection, calibration or training in the operating room, and also only uses a single sensor, so there are no auxiliary sensors required. In our phantom study as well as in our paired data study, we saw that our approach is able to generalize to unseen scenarios. Also, something we discuss in the paper is that we see potential applications to the rotational degrees of freedom. In the future, we plan to extend our approach to the compensation of orientational error. Also, we want to incorporate feedback of surgeons who are using the system to work towards a hybrid navigation solution, including X-ray imaging as well as electromagnetic tracking. And with this, I want to finish my presentation, want to thank you very much for your attention, and I'm looking forward to a fruitful discussion and, of course, to your questions.